Okay. Uh, Hello to everyone. So we can start and we will continue our seminars and our course in general. Um, I, I will start with some example and then we will discuss our steps of our project and we'll discuss your progress and we will discuss uh, your software. Okay. I will start from the software here. So I would like to show. Yeah, maybe I should tell the idea. So we have discussed uh, the plan in general. So uh, the the first task and the first part is to write a code that find their Nash equilibriums in pure strategies for given matrices of payoffs or utilities for two players. It's okay, but it might be generalized to several players. But we will start from the case for two players because it's slightly easier. Okay, so there should be a program software and input it will be the matrices and output um, Nash equilibriums in pure strategies, not a mixed one. The second part, the second task, if we are given a network, or if we are given a graph, create such matrices of payoffs and then find equilibriums and so on. The third part is to download or find anywhere else data about roads, traffic, whatever, and try to use it as a graph. The main problem here is to choose and then check formats because it might be a list of ages or it might be adjacency metrics or many others. And sometimes it's not very funny thing to convert from one data to the data that are accepted by this network's software library. Then we will talk about uh, several equilibrium or several players here, games, okay, and then we will discuss several players here, maybe several equilibriums. We will discuss it. Maybe we would like to create software right now for these games, and then we will discuss some more complicated things, considering uncertainties and so on. One of examples might be in this situation. Well, I don't want to claim that this is the perfect code and that it is um, correct, even that it is correct code, but it's a good example of the main idea. So you will check, you will test, you will write a code, optimize, and so on. But I will give you a general idea. So let's look at the example. It's a part of our project here. So first, I fix their number of nodes, number of cities here, and I create matrices of distances there, like here, from 2 to 20. Okay, uh, it's good. It's very comfortable that we have full graph or complete graph. So we can reach from one point, another point, um, always. Maybe for additional price, but the graph is connected. If it is not, maybe it's not so interesting here. It also helps us to use Floyd-Marshall algorithm to find distances. If we have adjacency matrix, our matrix with weights, so we know the cost of transforming, not transforming, for customers to go from one point to another, and then we can create distances. So it's like a transitive closure. Here, there's some code here. Okay, we create this matrix. It's not the matrix of payoffs, of course. We will create a matrix of payoffs. Then we create function. I have described it. So the idea is to calculate utilities. There are several ways. Here we think that all customers, they prefer to go to the closest shop, the closest store, and there are a number of customers here. The same number, so here it's 1. We assume that we can split. So it's not one customer, it's like 1,000 customers or 1 million customers. So we don't use any discrete properties. So it is like continuous properties. Here we have 2-player game. There is a function f that takes a matrix of distances and 2 indexes. These indexes are indexes of shops or strategies of players. Yeah, and payoff. Yeah, and it is allowed. Here it is not allowed. This one, this part of code, switch off or switch on situation when we allow several players have shops at the same city. Maybe it is not allowed. Why it might be not? Because it might be that there is only one building for shops in the center of the city, for example, and they cannot do at the same time. Why? There might be that one place his shop there, his or her shop there, and another player plays his shop everywhere else. So this one is switching off or switching on, and we might want to check what is the difference, and we will do. Okay, here, and the result is just payoffs, but for specific choices. So if we have given positions of shops, we know payoffs for players. Well, then we create matrices. It's payoffs for first player and for the second one, and just very, very direct way. It's just 2 cycles. So very direct way. And then we use some drawing tools to create matrices of payoffs. Here. This one is payoffs of the first player, and this one is payoffs for the second player. We can check, maybe it's too large, 10. Well, I use Colab Research Google, but I have Anaconda on my computer, so yeah. It's for how many? 10 nodes here. As you can see, so here we have 0 for diagonal situation. So it's strategies of the second player and of the first player here. And you can see that the best case for the first player is 2 here, and 8. The strategy number 2 and 8. Well, to say it precise, more accurate, it's not strategies that are better, but it's just cases. So this case 2-1 is better for the first player, and 8-1 is better. So in this case, the situation is preferable for player 1. So, and the same for the player 2. It's like symmetric one we have discussed. Zero-sum games. It's here. It's this game is of class zero-sum games, but we have not zero in the sum, but some constant. To say accurately, it's not the same as a zero-sum game, because there are some equilibriums that pay attention to the specific numbers here, and this constant does matter. But here we don't take into account such things. It's from epistemic game theory. There are some things that use this. I would like to show, because we would like to be very contemporary. So the idea is that players, it's equilibrium. It's like when player cannot choose pure strategy, but he tries to choose pure strategy, but there are mistakes, like a noise, and this noise may be proportional to their utility there. So it might be that the larger, the better strategy, the larger probability. And in this case, zero or constants are very important, because I will skip the details, but anyway, it looks like very symmetric. And we might want to find equilibriums. That's equilibrium in pure strategies. Okay, we use code that we have written before. My version, or for example, any other version, it's no problem. There are many libraries. My colleague mentioned that he knows several of them more than I asked him to. It's a PhD student here in Moscow, so I asked him to send me. So if he send me, I will share with you, so it will help you to do this. But it's not necessary. So our course might be good and successful even without these libraries, because the main idea of our course is not the tool of calculating Nash equilibrium. Okay, it's not something new or actual, so it's something that might be done in other courses, for example, in courses of game theory. But our idea is to combine many parts to make a very complex situation. Okay, so and our algorithm, in this case, my algorithm, he found 4 equilibriums. Well, symmetric ones. It's very natural, because we have very symmetric payoffs for players. So it's very natural that this Nash equilibrium is symmetric, but it is not necessary. Maybe not. For example, one player can put his store in the city, and another one he wants to be somewhere near another city, but diagonal is so good for one player. Well, we will discuss it later, but symmetric here when we restrict here our payoffs, that they cannot put 2 stores towards city, it still might give us not symmetric here. Okay, and that's all. So it's just a part of code from our last idea. Let's check, for example, several Nash equilibriums here. Let it be 2 and 8. So 2, 8, what it is. So we have 2 here and we have 8 here. Let us check if it's true. Well, 2, 8. Sorry. Oh, here 2, 2 and 8 here. This picture can help us to find Nash equilibrium even without any algorithm. I mean, here we can find Nash equilibrium just looking at this picture. At some cases, what is the condition for Nash equilibrium? There is a Nash equilibrium here. Let us check. What are strategies for player number 1? He can change the row here, so he can, if this strategy of the second player is fixed, then, sorry, I'll check, yeah, then the first player, he might want to change his strategy. But as we can see, this one is more preferable than all other values in this column. So this one is 0, this one is not very high, so we can see that this one is like a more yellow here. So for the first player, this one is okay, some kind of stable because he doesn't want to change it. Let's check what if it is good for the second player. Then we go to the next matrix and check here. Okay, it's yellow. It might be that this yellow is also very preferable for the second player. In this case, he might want to change this. But if it is not larger here, the same, then the second player might want to stay here because he has very high, like maybe 9 here, and it's okay for him. In this case, this place, oh no, sorry, not here, not yellow. Yellow is for the strategy first, but the second here, I hope that you can see this cursor here. And the second player, he has this value here is very high if we consider other values here. And you can see that this yellow things, so where payoffs are high for one of players, are not Nash equilibriums here. At least it's just the first Nash equilibrium, 2, 8, 2. And we also have 8, 2 and 2, 8. Let's check. 2, 8. 2, 8 here. It's strange indeed. But yeah, like here, because we have the same strategy for the second player. It might be if we consider not strict Nash equilibrium, like I think I do here. Yeah, it's not strict. In this case, here and here we just have the same value, and if player he is at this situation, players they don't want to change it, and in this the same. The same. The values are the same for players, and we think that this case might be the Nash equilibrium and this one, and the same for the player number 1. So we have here 8, 9, same values. Let's check what will change if we switch off this feature and we allow players to place 2 shops in one city. Okay, we can do this. Here and here. As you can see, now we have diagonal ones, not zeros. Okay. And what are Nash equilibriums? Okay, we have only one Nash equilibrium here. It's a symmetric one, and it's here, here. This one. So if there is no restriction, players prefer being in the situation symmetric ones, 2-2. There is only one Nash equilibrium in pure strategies, not strict Nash equilibrium. And this is an example of two first steps of our plan for our project. So we use code for Nash equilibrium, we use graphs. Yes, we are given graphs, and then we will need some real graphs. There will be some problems with this data because there is a joke that at least half time of working hours of machine learning specialist is not just for learning. It's just not for programming the neural network itself, but just to cleaning up data, because he wants to find the best examples for this neural network. Okay, and then we will go next. I see only one student, so yeah, and we can discuss your progress. And so you have already a code for Nash equilibrium, I know, and you maybe have a code for graph and payoffs, but I don't remember. Well, I don't know if you have connected these two steps. Ilya, do you have a code that connect this graph with a given graph with a Nash equilibrium software? Have you, Ilya?
Yes, I have code to finding Nash equilibriums and graphs.
Oh, cool. Please show.
Okay. Here we first construct two matrices of payoffs.
Okay.
And then find equilibriums.
Okay. Nice. So, where is the place where you use graph? Mm-hmm. Graph.
Here we find
Okay.
photo space and then use them to find payoffs here.
I understand, but in this case, as I can see in code, there is a part of code that use 4 players. There, it's not a universal thing. So, do you use range? I see. Yeah. I see. Sorry. Yeah. I understand. So, okay. Nice. Great. So we can move to the next step. So if it's okay here, maybe do you have any database of roads or traffic or any other things that we can use as graph here? If not, I will give you. I will give you a link.
No.
Okay. I will give, in chat. I will share this. So that's okay. Sorry. There is special site here that I like. This one is this. Okay. Good, good. Please check our discussion, and there is a link there. It's from Colorado University, Index of Complex Networks. And you can choose here subdomains and graph properties and size and so on. For example, okay, I will show. Yeah. Okay. 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 So, yeah. And then you might want to find like here roads, for example. I don't know if we need something else, maybe airports, but okay, roads. Okay, yeah, and we have no. Maybe you should apply this one. I don't know where. Okay, check. I think we should change something in filter because we need to find. Okay, I can try to do it in my situation. Sorry, here. So now I share my screen. I will try to do the same as you do. So okay, networks, transportation thing, subdomain. What kind of subdomain? Roads, the same idea. Okay. And okay, networks found. Let's check. Yeah, and what I have here is the result of traffic here. You might be now already have this one, maybe not. If not, please let me know. So because it's a very straightforward way, just transportation and subdomain here, and then we have some statistics here. I recommend not using a very large network for the very obvious purpose because it's too large for computer and there is no any additional value for our course because we just need to find to test our idea and to combine this mechanism. We weight directed or undirected, it doesn't matter because we always can assign some directed. Well, our algorithm maybe okay. I'm not sure about Floyd Marshall. Is it okay for directed? Yeah, I think that maybe it might be applicable there, but we should be careful because some algorithms they depend on directed and undirected. And now we can find roads. For example, we want to find roads for Barcelona traffic. Here, what about Barcelona? We have about 1,000. Yeah, and when we talk about real data, we might want, as I have told before, not allow players to choose any city, any of these 1,000 cities, because it's too large. We don't need this one, and we might want to fix maybe available cities for shops. It might be 2, 3, 5, 10. And in this case, we can use very large networks, like 1,000 points or maybe even 1 million ones. It's just the complexity of this metrics for distances. But for our Nash equilibrium, we might need to check smaller numbers. Okay, it's Barcelona. What else? Maybe United States. United States might be too large. Yeah, United States. Well, if you have very strong computer, very powerful, you can want to have. Oh, they have divided rods for every state. So if you like Kansas, or for example in New York State, maybe you want to use it, and so on. Rome roads. So your task and task for other students, if you're present, and it will be a task for them when they will be present, or as a homework to choose of Paris. I like Paris. You try to download this data and create a graph using this data. Not specific this one, but or whatever you like, and then try to find Nash equilibrium in this city. So you use this data, you create graph, and you just apply your algorithm. Okay, is it clear?
Yes, I can do it.
Cool. I don't know how much time you need. Maybe 10, 15 minutes. 10. Okay,
Maybe.
or 15. I don't know the complexity for you, but let it be 10 maybe to test something. So 10, 15, a quarter past 10, and then we will discuss your results. So we will discuss it 10, 15. The database and the Nash equilibriums. Okay? Okay. Okay, now it's 10:30. What is the current status? Have you downloaded and tried to find Nash equilibrium? Yeah. What data set have you chosen? Ilya, are you here? Okay. Ilya, do you hear me? Are you ready? Okay, I think that it might be useful to use 10 more minutes to do this. So up to till 10, yeah, 10:30. I will try to check at 10:30. Okay. Ilya, have you done this task? Ilya?
Yes, almost.
Okay. How much time do you need?
Maybe a couple of minutes.
Okay. Maybe 5 minutes or 10 minutes? 10. Fine. Okay.
Okay, maybe.
10, but if you are ready, you just let me know about this. So you write in chat or tell me, and we will discuss it. Okay?
I think we can discuss it now.
Okay. Great. Please show. Cool. Rome. So you
Okay,
have chosen Italy. Okay, nice.
yes. So
Mhm.
we have the each list like this.
Okay, Rome.
Here's some meta information, and here starts the edges.
And excuse me, nodes are cities it's in Rome. So nodes are buildings or what nodes? Do you know what nodes are? The city vertices. Oh, intersections.
It is
Okay. Nice. Okay.
okay. So we just
Mhm.
create a graph from this. We
Cool. Oh, so you used a direct way. So you just read this file line by line. So it's okay. I mean, you know, of course, that you have some tools to download to use data from file and directly convert it to the graph in NetworkX. Not all the time.
yes, but it has some
Yeah, I understand.
strange format.
Yeah. It's okay. Okay. Nice. Cool.
So then I choose 10 random spots
Okay.
where
Cool.
then I compute the distances from every spot to every other node with Dijkstra algorithm.
Okay.
So matrix array is it has only 10
Okay.
rows for each
Okay.
spot.
Cool.
And then I just reuse the
Mhm.
code from the previous.
Okay, we have two Nash equilibriums here. Okay. And okay. And as I see, you don't have a restriction that they have no opportunity to place two shops at one intersection. But these players, they have this opportunity, so they might want to place two shops at one intersection. Yeah. Correct?
Yes, they
Okay.
can do this, but
Yeah.
then they
Okay, but it's not a Nash equilibrium.
yes,
Okay. So a symmetric case is not a Nash equilibrium. Okay, nice.
actually that is strange.
Uh,
Uh,
it might be in some games, but
I think the matrices are looking strange because there should be number of customers.
okay. So maybe something
There
wrong.
must be like
Oh, mm,
it's when we think that the
yeah,
one
I
customer
understand.
in each node.
And okay. Well, I use the special vector for to set up their a number of customers at each node. I used I don't remember. Yeah, it's the vector b,
Yes.
capital, and payoff. Yeah, okay. Now it looks different. Oh, and there is another Nash equilibrium. So now we have symmetric case 3-3.
Yes.
Okay. Cool. That's great. So now you have a code for this, and already you can create some kind of investigation. So you can check cities, you can make Monte Carlo or something, and you might want to switch off and switch on these restrictions and so on. Great. Now I would like, before this break, to tell more about equilibriums, maybe some more ideas about this, and about uncertainties. So later we will use uncertainties, and I think it's a good time to tell about this, and then we will discuss it in details. But for yeah, and I will tell what we can, how we can improve this code. I mean, not improve, but how can we add more features to this code. Okay, nice. Okay, thank you. That's great. Yeah, okay. Now we are here. I will use special file here. This. Okay. Okay. So now we have matrices here, and we know how to calculate Nash non-strict Nash equilibrium. Yeah, and you can check a strict Nash equilibrium. So in this case, if you have two utilities with the same, it's not Nash equilibrium because we have another one. But okay, it's not necessary here. What I think is very valuable to cut off, it's like there is a special name for this. It's like rationalizable, yeah, rationalization. And this process is used in epistemic game theory. As a basic thing. They use mixed strategies, but now we will try to check if we can apply it here for pure strategies. So it's not completely the method that they use for epistemic game, but it's the same idea. The main idea, I have described it, but we maybe would like to tell it about this again. So maybe some strategies for this agent or for this, for example, for this one, are so bad that there are strategies, or there is at least one strategy that is strictly better or just better than this one. For example, we have for x, y here, strategies here, and this will be index. Wait, no, y. Index will be here. Yeah, and we maybe know that there is some other strategy for second player, such that this function is greater or equal than this one. In this case, we don't need this one. I mean, if we assume that player 2 is rational, then we might assume or suggest that he will never use this strategy, because in this case, for the same strategies of the first player, he will get the same profit or better than here. It's very easy to check. I mean, we can find, we can create a cycle here, for example, or use a vector representation. Sorry. So I will write it here. In this case, we eliminate, delete this strategy from the set of strategies. So we might want to use special vector or vectors for every player to hold their information about available strategies. So now we have just strategies from 0. Oh, well, we have, but we almost do this list. So you did it when you have randomly chosen spots. So it's exactly the same. So you have a special list. Well, not vector. Okay, list. It's even better because you have a different size of this. So you have a list for available strategies, and this condition will just eliminate one element from this list. It might be that no strategy can be eliminated, but sometimes such strategies might be eliminated, and I will discuss which one. And then you can do the same for the first player. It's easy to see that you might want to create this situation. X. Sorry, it's like a G, but X, and so on. And maybe it look intuitively, it looks like this process will have only one step, but it occurs that this procedure may have several iterations. So after you delete one strategy, then maybe something will change. And in this case, you will need to do this step several times, and then check what will be the lists of available strategies there. Why we need to do this? Well, and is it true that we can find such, and when can we find such games that we have such condition? Okay, let's see metro, the simplified map of metro stations of metro of Moscow, like here. It's very simplified, but it's easy to see that yeah, but if we allow well, not easy to see. Maybe here we don't have this one because maybe have. So the idea is that this strategy to place shop here, this position like X, and maybe we want to place it here, and it looks like this one is always better. Why it is so? Well, when you place Y, the strategy of another player somewhere here outside, for example, here, and you want to place to change your strategy from X to X star, in this case you will have the same customers here, but you will lose customers here for this player. So it's not very good to go to this line deeper. So maybe you want to fight here for these customers. Okay, it's normal thing. In this case, it's also the problem that if you want to change your city from here to here, then maybe this player, he will change his strategy here and place his city here, because they change. Well, they choose their strategies simultaneously and independently. So if you choose this strategy, the player 1, then the player 2, it might be the case that he will choose this strategy to place here his shop. In this case, he will get all these, and it's not good then if you put your X here. But it depends on number of cities here. So it might be the case, it might be not, but we should check. But for several cases, we can imagine a situation that going from this place to this direction, in this direction, is not very good. And what if Y will be not here, but here? For example, you decided to place your shop not here, but here, and here there. Well, yeah. So it doesn't look like it's a good strategy here. So and we can check if it is true. So it might be the case that we can reduce the spots of our strategies only to these nodes here, this circle. Maybe not, but it's a good thing to check if it is true. So this process here, he might give us some information. So he will provide us with spots that are not interesting for any player to choose. Okay, and it is very easy to see. So I'd like you to create it as a task to check if there are strategies that can be eliminated here. And another thing, I think 3 minutes, okay. Task 2 today is to check, well, min-max strategy. Yeah, min-max, max-min strategy. Well, for this specific utility function, it might be that it's the same as the Nash equilibrium, but it depends. So, and max-min always exists, though Nash equilibrium might not exist. No, what is max-min? The idea is that, for example, you want to check to find this equilibrium for the first player. For the first player, then you create. Well, you calculate the worst situation. So if player 1 he choose this, this strategy, what is the worst situation? What is the worst strategy for him that might be chosen by the second player? For example, this one. And for this strategy, this one is the worst. And so on. And then this player 1, he compare these numbers and say, okay, here is the best for me. It is important, and we will discuss it after the break, that there is no information about the second payoffs of the second player. So no information. If it is not zero-sum game, then something will change here. And we can do the same for player 2. And find, for example, this one. And this will be the solution in max-min equilibrium, or max-min domain, something. There are different names for this. And the task will be to create software for this and check if Nash equilibrium equals these specific situations. Okay, now we have 10:50 our watches, clocks, and we should have a break, and we will meet at 11:10, and we will continue our discussion with Max Min and this epistemic game theory rationalization idea. See you in 20 minutes. Okay, we can continue. So there is 11 and 10. And I would like to introduce, to describe again the situation with the best response. And some application of this to our problems here. But before that, I think, well, I like our results for Nash equilibrium, for graphs, and maybe we should add here uncertainties before we go to n players. So then, but I will start with best response. So the idea of best response, as I told, that if we have a function, for example, for the first player, and if we fix all other strategies, we can get, and we want to maximize it, a special function. Well, it's best response for the first player. It will use this fixed strategies, all other players, and it's argmax. Of course, there should be, well, that might be the case that it's not argmax when we have only one value here, but argmax when we have several values. It depends. Maybe we should check situation when we have several maximum values, but we will start our talk from the beginning here, from the situation when we have only one maximum value. Is a max of this function. This function using x1. And if we combine them in one system, the same for others, and then we here denote x that equals best response as x wave, we will get a Nash equilibrium and pure strategies. So directly, this one will be Nash equilibrium. If we have several values here, then we might want to check all possible situations. So we might want to look at this as a set of values here. So now we have set here, and we just try all variants for this. It's not so easy, but the main idea is the same. So we have here several variants, so we check for everyone, for everything. It's conception of best response. The idea, the first idea here, is that we can create a process such that we can start from, it's like a genetic algorithm, but it's not, well, it's very trivial genetic algorithm. I'm not sure, maybe not even genetic ones. So we have here the situation like here many. So we place stores, and we then would like to check what is the best response. Best response here. It's not an equilibrium yet. It's just the best response of the first player for this place. It might look like I placed my shop, or you place your shop near Kremlin or somewhere, and then you check surroundings, and you understand that it's better to change the place to sell this building and to buy another one or rent another one. And all players, they think the same, and they try to create a new position. Of course, if they are the same, then we have Nash equilibrium, but maybe not. In this case, we will have maybe infinitely many such values. Well, not values, but it might be that we don't have here Nash equilibrium, and we don't have such equivalence anywhere. So there is not such a case. There is a special case here. So we consider not the situation, when a player, he changed the shop from to the best response, but the idea is that he have some kind of inertia, so he doesn't want to change it's very fast. For example, if we have graph somewhere, and this one, this is x1 0 here, so it's the initial place, and then this one is the best response. And in this situation, we might think that this player, he cannot just jump here from this point to this point, but he choose a node that is very close to his previous node, and in the direction to their best response there. This idea. Or we can find this function if we have here a restriction. So we might want to restrict agents to find. It will be like a greedy algorithm or somewhere. If we restrict him to change his strategy only by one step. So there's not argmax for x, but x such that of previous one. So there is. In this case, we will have a greedy algorithm. I'm not sure that it is well described and investigated, so we will try to investigate it if we have enough time. This version of our game here. Okay, it's best response. So the idea that we can apply right now, for example, I mean, we have all necessary tools. If and check what is the process of best responses for these two players. What will they choose? So we start with some point and then check. Converge or no. But it's not everything about best response thing. There is also conception of double best response, but we'll skip it right now. I would like to tell more about uncertainties. So, okay, as I described, we can describe uncertainties like structure, in terms of structure of possible words. So it's an agent, like the first agent, and he has two alternatives. The first, graph 1, and graph or game here. Game 2. Let it be graph here. Transportation graph. For example, we might imagine that in Rome we have many roads, and we know that the authorities of the city, they have plans to stop traffic from this point to this point. But they're not sure about timeline of this. So it's some kind of gossip, and people discuss this opportunity, but no one knows exactly if this traffic stop or not. It will depend on some laws, some federal government of Italy, and so they don't know. But so they have to consider two possible graphs here. This one and this one. And if you were in Rome or France, you know that there are a lot of streets that are repairing. So there, well, maybe not the traffic maybe is not stopped, but there are many reconstruction there in the center of Rome and in Toulouse, I think, but in Rome, and it's very easy, and in Moscow, of course. So it's easy to imagine the situation. For example, for metro stations. Okay, we have graphs, and we can add here. We consider two-player game. For this possible words, two agents. So this one, the initial agent, and this one, his opponent. And these opponents are different because they work in different situations. Here, we might think that, for example, the second player, he doesn't know too. So in this case, we'll have only one instance of the second player. So they have the same uncertainty. But maybe the second player is government, and they have some shops that are owned by government of Italy or Rome. And in this case, they might know these plans, or they have some idea how they can make these plans possible, and they are sure that they will win, or they are sure that they will lose, for example. So they know exactly where they are. So if this graph is really true, if it's real, then this player will have no uncertainties, the second player, but the first one has such uncertainties. And the same if, for example, we have another graph. This will still, well, the second player will know. And in this case, the correct answer, but player one, he doesn't know. And we might want to create, well, to find an equilibrium here. Okay, and in the same idea as here we have for this system, as we have here, of best responses. So let's imagine that we have, we will denote now the upper will be not time, but now enumeration, it's a number of, it's just index of this instance of this agent here. Here and here, and here we have this one. The first is instance. Well, we might think about these agents as the phantom agents. So some of them are only in the imaginary, they're not real. They're only in the head of another player. For example, in this, if this situation is real thing, then this player is real, this one is real, and this one is just an imagination of the first player. So there is no such player here that will act in this graph. It's just an imagination of the first player, because the real one is here. And they have their, well, for our case, if we have no uncertainties, the situation is the following. So we have two players, and we have one possibility, one graph. It is something that we have already solved. We have found this equilibrium, and we have equilibrium, information equilibrium, it's all the same. Here, we know how to calculate this one. But we want to calculate here. or here, for example. And we might want to do this, but if usually when we talk about best responses, we say that let's imagine that other players, they have already chosen their strategies, and then what is the best strategy for this player. But here, since he has uncertainty, we can say that the player 2 has already chosen, for example, strategy 1 and strategy 2, and what will agent 1 will do in this situation. So it's strange. He should become crazy about this. So it's not a good idea to introduce the conception of batch response in this way, but we can use here a function, utility function. So and understand that it's just argmax here, and go from the definition to find this situation. So so the reasoning of the first player is the following: let this graph is real. In this case, let's imagine that the second player will choose this strategy, and that in this case he will choose this one, and player 1, he doesn't know which one is real, so he might want to choose at least 2 different ways of considering this. The first one, he want to apply maximin here. So he want to find his action such that his utility function of this action, and well, say this one, his utility function of his action that he has to choose, and action of game of second player in this game, and his utility function for the second graph here. So it will be this one, and graph. We can mark it with graphs. Mean, yeah. So in this case, and this will be the decision of the first player. So he thinks that his that nature or that nature plays against him, and he want to find the safe variant. So if this one will be true, and if this one will be true, he doesn't know, but he might choose his action such that even in the worst case, he will get the maximum here. This one, the first conception of it. So he always tried to choose the best strategy for the worst case for him in this situation. And of course, we can create here the system. We can create the same for all these variants of choices. So we have here. Since we don't have here uncertainty, so the minimum here will be just here G1, G2, and we have here the same strategy of the first agent, and we want to change strategies of the second player. And the solution of this system, and we can use this process as well for this. But the solution of the system is equilibrium here. Well, some people, they call this or refer to this equilibrium as informational equilibrium or reflexive equilibrium. But the main idea that we have uncertainty here. Okay, what is another approach? Another approach is to assign probabilities here. For example, we can imagine that this variance, they are not, well, they have, there is a probability distribution, and it might be not the real ones, but in the imagination of the first player. For example, he thinks that the graph G2 has a probability 0.8 and this one 0.2. Of course, here we have ones. It might be not the real cases. It's just his imagination about this. So, but he assigned these weights, and we can think that it's always just equal here probabilities, but maybe not. So we are free to choose whatever we want. For example, if we talk about combinatorics here, so we might want to calculate the probability of some event, several events, and then the probability of such event will be the weight here for this age. In this case, it's a little bit easy because we will use here like the same here, but not minimum, but a linear combination here, like here. Yeah, I hope that it is clear what I mean by this formula. So there is, for example, if you had here a utility function like x1 plus x2, and it's for graph G, and he had for graph G2 like x1 plus like here, then if we have probabilities like 1/2 here and 1/2 here, then we have like a function here. It will be okay here for. So he will act as if a function is equal to this expression. It's simply because we just we can use our solution here. So we don't. A minimum is not very good function for analytical optimization, because if we have such situation, that might be it might be the case that we have an analytical solution for the maximum of this expression. So we have to find derivative here, and we will have solution here. For min-max, it's much more difficult. For example, if we have utility function like a parabola, and we have two parabolas here, like this one and this one, then we have to calculate this situation. Oh, we want minimum. So we have several points to check. For example, if you want to have to think about maximum, so the first one is the first one here and the first one here, we don't want which one is the worst. So choose like, well, it's another thing here. But sometimes we might imagine a situation when they have something not so easy. So there might be several tops here, and then we have to check. And even here, we have to create this point as an intersection and so on. But for this situation, when we have probabilities, we will have just another parabola with another coefficient here. So it's slightly different from here. Okay, but here we are ready to find equilibriums. Well, in this case, it's not so easy to find this equilibrium, but we can try, and I think we will succeed. With this, it will be maybe even next task here to create such thing. So, well, not so the first task is here, check epistemic game theory, if it is applicable here. Then we can check maximin here. Then we can check best response. What about this process? Converge on, or it doesn't converge for two players? Yeah, okay, here. Then we can create this one. Yeah, so when we try, when in this process we apply greedy idea and we restrict players for changing their strategies, not to the new best response like here, but to another thing. So the optimization here is restricted by their some area around the previous point. Okay, it's task 3. Well, this one, task 3. This one is task 4. And then we will go here and we will try to find informational equilibriums. Yeah, I think this plan will be better than the previous one, because when we have two players, we can draw many good diagrams, many good figures. I was impressed by the situation that we have got. And then we will add more players, 2 players, 3 players, and so on. So this is the plan. Let's start, well, I think it's clear what we should do, at least first several steps. So let's start from the very beginning. Yeah, I would like to ask you and other students, if they were present here, to develop a code to check this process. So if we can cut off several strategies in this matrix, for example, for Rome or for any other graph, but maybe for Rome, you'd like to. And then, yeah, this one, check the maximin, the point of the points of maximin here. Yeah, and for maximin, maybe, well, yeah, it might be the case that we will have several values the same. So for example, here we have 10 and here we have 10 and it's maximum. In this case, we will have several solutions, several equilibriums. Okay, so I think that how much time do you need? Maybe we will start step by step, task by task, and about, well, 10 minutes for each task. I don't know if it's too much or if it's not. So, okay. So now we have 11:40. Oh, okay, and we will discuss at 11:50.
Can you please remind how this elimination
Yeah,
rules
okay,
work?
okay. Wait a minute, I have a phone call, but I will. It was spam. Okay, I will give idea. Yeah, it's an important part. So when we have matrix, or functions, yes. And then let's imagine that we have lists like L for the first player and L2 is a list for the second player of available strategies. Like in Rome, you have chosen 10 spots here, here, and here. So the ordinal is 10. And then we check a condition. So if it's true that this column is smaller than this one, we will do it by element by element. So we will check if this one is larger than this one, if this one is larger than this one, larger or equal, or this element is larger or equal than this one, and so on. And if we find out that this column is weaker or not so profitable, we eliminate. So we make our list smaller. Maybe not by one column, but maybe by several ones, so we can get just, sorry, like here. So we will have a small list. And we do the same for the first player, but for rows and for another matrix. And then we will have iterations. So we have initial sets of these strategies, and then we will have, after such elimination, strategies, new strategies, and so on. This process will converge definitely, because, well, we can prove it for finite, and we always have we cannot eliminate all strategies, because there should be at least one strategy that is better than others. So we will have at least one strategy here, and at least, so it's not 0 for an AT here, and it's converge. So there exists T such that T equals this one, T plus 1, if T larger than T. So this process will stabilize. And the result will be the infinity, the stable version of this a list of available intersections for Rome. So you have chosen, let me have Rome, and we have several intersections, and we say that this is the part of L1, 0 for the first player. Yeah, of course we know that we can have different spots for different players, but let's start, for example, from the same spot. And then we will eliminate, and we will have smaller set. For example, one intersection is not reasonable to be chosen. For example, it's somewhere, I don't know, somewhere else. Like here, it's very difficult to find the reason to put your shop at this spot. Why? Maybe you should place it here or here or here. This one doesn't look very reasonable. Okay, so this is the idea of this process. Is it clear?
Yes, it's clear.
Okay. So please use next 10 minutes to create this code And we will check, for example, for Rome or for any other graph, if there such elimination of strategies. Maybe there will be no such strategies, and this initial set equals the last set. So it will stabilize from the very beginning. I don't know. We should check graphs. So now is 11:45, so we can discuss it at 11:55. But if you will be ready before this, please let me know. So it's just for it's some kind of deadline, but it's soft, so we can extend it as long as we want. So we can extend it several times, but just for some help, for more certainty, let it be 11:55. Okay. Okay. Okay, so we have 11:55. Ilya, so I think you're not ready with that task, yeah? But I would like to share some information about this concept of rationality, of epistemic game theory, and so on. Emmanuel, hello. So I would like to say that we proceed with our course, and we have completed several steps, and now we're talking about some new equilibriums. So we have downloaded a data set from Rome, and we tried to find equilibriums, and we found equilibriums for Rome here. So a conception of epistemic game theory, well, that I use was created, or he wasn't. It's difficult thing to say if it was created, but it's usually associated with Andreas Perea, Professor Andreas Perea. He's great, and he in Maastricht, game theorist. He has a special book. He created courses, and he has a new book. Okay, and there is a mini course about epistemic game theory, and this process of elimination is described here. So we consider finite static game. Finite, okay, we have it's finite and a number of strategies. Static, well, it means that we don't have several steps, but our players choose the strategies only once. So it's static game and G. And there's the original one, and then we just eliminate all strictly dominated situation here. And there are theorems here. And yeah, some history about this. So it was created or discussed before Andreas, Professor Perea, by Bernheim in 1984, and by Peirce in 1984, and they have created a new term like rationalizable, rationalizability, and stochastically independent, correlated, and so on. Yes, and sometimes it's equal to Nash equilibrium. Maybe we'll discuss it, maybe not. It will depend on our time. But there is a connection of this procedure to Nash equilibrium, and there might be a Nash equilibrium in mixed strategies. But for this, we should have a tool to check if one column is strictly dominated by an average by a combination of other columns. I have shown some examples. So it's more difficult from terms of optimization, and I will provide you with algorithm as an example to make it simpler. And in this case, we will be ready to apply this. And there's a theorem here. This epistemic game theory to find Nash equilibrium in mixed strategies. But it might be later, and it's not necessary part of our course. So it will depend. But there's history in game theory. So he is on economic department in Maastricht. It's the Netherlands. So okay, we are back. We are back here. Ilya, have you any news? Have you?
I need some more time.
Okay, no problem. Okay, definitely. Emmanuel, have you any progress with that tasks? With those, Emmanuel, are you here? Emmanuel?
Yes, I'm here.
Okay. Have you solved that problems? Have you coded have you developed code for Nash equilibrium and for graphs?
Yeah, I started doing it.
Okay, nice. I would like just to show you an example that we have discussed with Ilya at the very beginning of this lecture. It will help you.
Okay.
So I have shown to Ilya this example, and it occurs that he already done it at home, so it was just an illustration and maybe a necessary illustration, but I think it has some advantage. I have pictures here, but yeah, okay. The idea was that we had specified the number of cities here, like m equals 5 here, 5 cities, and we create, like we did before, distances, and we created later the matrix of shortest distances between two, well, not shortest distances. Distance is already short. Okay, the shortest path, the length of the shortest path between two cities, and then we use it to find a Nash equilibrium there, and these matrices are those matrices that we will use in Nash equilibrium. So it's matrices of payoffs. How we might want to use it. So these payoffs for the first player. So if player 1, he chooses strategy 2, and player 2, the second player, will choose strategy 3, then the payoff will be green, so it's 3 or something. In the same case, if the first player will choose 1 and the second player will choose 3, in this case, the second player will get payoff 4 from the second matrix. And we can find here Nash equilibrium. So the color of this element here should be the brightest among all other elements here. For in the okay, let's check, and I found here Nash equilibriums are 2 and 4, 4 and 2 symmetric ones, and I had special restriction here that it's impossible to place two shops at one node, at one spot here. So in this case, utility will be 0 for both of them, so it's impossible one. And 2, 4, so 2 for here and here. And now we will check if it's really a Nash equilibrium. Okay, for the first player, 2, 4, the first player can change only rows. He cannot change columns. So this one should be the brightest, or should be the yellowest color here. Yeah, it is, because all others are violet or blue, so it's the brightest thing. Okay, nice. So for the first player, it's the best variant here. It's okay. For the second, this one is also the brightest here in this line. So the second player, he doesn't want to change his strategy. So this is Nash equilibrium here and symmetric thing here. We have solved and we have checked. It is really so. Yeah, yeah, 2, 4. Okay. Okay, it is clear. And then we have, so we have tested it. I did it for larger things, so you can check it for maybe 50 or even more. I don't remember 100. I think it's okay, no problem. Yeah, but very strange network, but okay, maybe 100 is too much. Okay, but 50 was okay. Okay, let's check 50 because it's too large. Okay, and we will have here. I was sure that it was done before, not 50 as well. Okay, then to 20. Well, I'd like to show you the largest situation, but it looks like 50 is too much. Okay, yeah, 20 is okay. It's for 20 cities. We have here. We might want to try to find Nash equilibriums here just by looking at this. But our algorithm shows that there is no such equilibriums here, unfortunately, here, for this random graph. There is no such element that is optimal for the first player and for the second player. And we can check it for other things. So that's what we have created by, that was created by Ilya. Not the same, but a similar thing. And I put on as well. And then we downloaded. Well, Ilya downloaded. He chose. And Emmanuel, maybe it's a good idea to choose for you. Well, graph here. So there is a link here in our chat. So icon of Colorado, it's from Colorado University, and there is a networks there. There are networks, and we chosen transportation networks and roads here, and we found 40 databases. So we found there database of United States roads, Barcelona roads. We found database for United States roads for every states, Columbia, Kentucky, Kansas, and so on. And there are many nodes there, intersections. So for example, here in Florida, maybe, I don't remember the abbreviation, but it looks like it's Florida. We have 1 million nodes. One node is in an intersection between two or more roads here. So and there is a page link here, so you can download all roads in this state, and then you might want to find an equilibrium there and so on. So it's better if you choose another database than Ilya did. But Ilya he has chosen Rome in Italy. You can choose any other. London, maybe Philadelphia, Birmingham. Not so nice city, but it's great. I like Great Britain. And so you can, for Sydney, try Berlin, Germany, and other things. Chicago, Broad, whatever you want. But you should think, and it's a real thing. So it's a real data. Pay attention to the size of this data set. So maybe it's not a very good idea to choose very large data set, because maybe you don't have such a strong and powerful computer. For our exercises, we don't need very large networks. So Chicago maybe is okay here. And the problem here will be, it might be in different formats. For example, Ilya, he has shown that for his database, for his Italy database for Rome, there were comments in the beginning of that file that prevents from uploading this data directly to the graph. They had to write a special code to decode this. So I can help with this. So sometimes, usually it's not a problem, but there are difficult cases sometimes. Okay, so it shouldn't be very large, but it shouldn't be very small. Just 2 or 3 nodes is not very interesting at all. Sometimes when we talk about Nash equilibrium, it looks like it's when we allow players to choose any spot here, any of this 1,500 is too much. So we can choose several of them. We can allow players choose only 2 or 3 spots, or 10 or 20. In this case, this matrix that I have shown, like this green and yellow, will be just 10 by 10, even if our initial network, is very large. For example, all rows in Chicago. But our matrix for players will be 10 by 10. That was the idea. Okay, so maybe if it's not very easy to write down code, but if you are working on this, that's great. That's very good. I will try to help you, but you can also try to find the network for you. So which network you will use in your work. And Ilya already done it, and we have discussed it at the first part of this lecture. It was very interesting thing. And now we are trying to create and to apply different types of equilibriums, like minimax or epistemic game, or rationalizable approach. And then we will try to do others. So you will see this all these things in this video. So there will be recording available for you. So you and I think it's important that we will try to be on the same level. I mean, not level, but on the same step of in our discussion of this software, because it will help us to discuss some details, because it's difficult to discuss different tasks in different times. So please try to do it. And if you need help, let me know, Emmanuel. So if you need help with every status, it will be great if you share your problems, and I will try to help with this. Okay, so if at some point you feel that you completely lost here, don't worry, just let me know about this. I will try to give you enough information to get you in this course again. So it's not a problem, it's just an exercise. Okay, now we have about 15 or 18 minutes before we break here, and we will continue next week. So the homework will be the same. So we will try to write a code for the first task that we have discussed already, and for the tasks that we have discussed today. It will be the homework. So we will try to do this. And the result of all these small homeworks will be that homework that I have described at the very beginning. So I've told that we will have like a project, a great homework, the software that will get graph and that will create equilibriums, something that we almost get right now. So we just improve it. So we almost done it. Okay. Okay. Ilya, are you ready? Not yet. Ilya? Okay.
Yes, I ready.
Oh, okay. Please share. I will. Yeah. Okay. I stop my screen. You can share your screen. Okay.
So that's how I eliminate.
Cool.
Then I just applied in cycle.
Okay. Nice. And so, were there any elimination at all?
Yes,
Oh,
I
cool.
think there's
Great.
one-step elimination.
Great. Nice. Wow.
Left with such matrices.
Cool. So, and you have started from the 10 spots?
Yes.
Okay, nice. So You have okay, cool. Okay. Later we might want to discuss this in details because it's interesting to know which intersection in Rome are not rational to choose and so on. So nice. Okay, it's very interesting here to discuss the result of this when we apply this algorithm to real data. But maybe not now. I don't know. But what if you choose different spots? You will have different um, different stable set of strategies after elimination, of course. What could you please show several other instances? Just execute it again several times. Okay. Cool. Okay. Okay. Oh, yeah. It's even not symmetric. Nice. So we have 5 spots for the first player and 2 spots for the second player. It's slightly surprising, but it depends on elimination. So if you eliminate simultaneously, non-symmetric thing. Is it a feature or a bug? I like non-symmetric things, but I'm slightly strange because intuitively it looks like if a player they start from the same sets, they should have the same the symmetric metrics. So it's slightly surprising, but maybe it's correct. But please check if it is so, if it's really not symmetric. And while you are checking, okay, maybe we should, before this checking, discuss their Nash equilibrium here for the same network and for the same spots. And this epistemic, some kind of equilibrium and or epistemic states after elimination. Is it true that for all these situations, Nash equilibrium are inside these possible these states and in these strategies after elimination? So you can find Nash equilibriums there. You have such code, and you know what strategies will be stable after elimination. And is it true that Nash equilibrium inside these sets, inside these lists, or it is not true? I expect, well, I suggest that Nash equilibrium will be always, all Nash equilibriums, they should be always in the lists that are stable after elimination, because there are some theorems and so on. But maybe not. I'm not sure. Can you check?
I had a mistake.
Okay.
I think, yes, it is true that it will be always symmetrical.
Okay, cool. But what about elimination? There will be will elimination take place here, or there will be no elimination at all?
Yes,
Okay. So we had started from the 10 element spots, and what will we have?
We get only 1.
Wow, cool. And is it the same as Nash equilibrium?
It's hard to tell.
Well, but you know the for Nash equilibrium, you know the optimal strategies. So the strategies of agents for Nash equilibrium. So you should just, or you can just calculate and compare, or you can just check if this 8 in the last list.
Yes, but I
You don't
save the indices.
Okay,
I
but
only save
we
matrices.
can now. Well, it would be interesting to check indexes, but right now we can check their value of utilities. So you have utility optimal here, so it's 1,676 and 0.5. But yes, and you can calculate for the initial matrix U1 or initial matrix U2. Yeah, this one. Yeah, cool. So you have found the Nash equilibrium by this way. That's nice. That's completely well. I don't remember. Well, it's okay with theory. So theory, it proves theory. Not it proves, but it. I don't remember. Oh, okay, that's great. Nice. So we have 8 minutes to discuss some things. Do you have any questions or ideas? Maybe Emmanuel, Ilya, do you have any questions about our tasks, about our plans? Any ideas? Okay, then we have 8 minutes. We can start with the next task. The next one is Maximin idea. Here. The idea of this task is, as I have described before, to check to find all values that are minimal in these rows for the first players. So let's imagine that we don't know our opponent. We know how how his strategy, how his strategies will affect us, affect our utilities, but we don't know his aims, his decision making, and so on. So we think that he will choose the worst strategy for us. For example, it's usually it is for military application because for the obvious reason, but we can use it in economic, like here. And then when we find such values, first player just find the minimum, the maximum of these values, and choose this strategy. So even if his opponent will choose the worst strategy after him, then the first player will have the best utility. This was an idea. For my code, I used like max or something, and pmax. Here, I believe that it will give you a vector, but I'm not sure, but a vector through this dimension, the first one of maximum values. And for the second player, we can use another direction, another dimension, and the same, so we can use this function. If there is no such function, we can just create a code for this. It's not very difficult thing, but I believe that there should be a function, and I use it in my code. So I have shared with you my code to find. Well, I give you an idea. So here, okay, okay, sorry, here. Where is it? Maximum is not, yeah, here. As you can see on the screen, so m equals np mean it's the maximum value here. Yeah, m for this row in this row, but I think that it should work on matrices as well alongside this dimension. But you can check, so some kind of part of exercise. Okay, here, and we will have here several equilibriums of this in this domain, and we might want to check this well, if they are the same as elimination or as a Nash equilibrium strategies. Well, the one idea here that will of course well, definitely differ, that for example we have, so it we cannot have situation when we have this element as a equilibrium in max-min strategy. This one is an equilibrium, this one an equilibrium, and this one is not equilibrium. We cannot get such situation in this setting. So if when we know all these strategies, like we checked this one is okay, or maybe several of them are at the same situation, if values are the same, and here. So we choose here not an element, indeed. We choose a set of strategies, like lists. And all these elements that are here should be at the same situation. So, but for Nash equilibrium, it's not true. For example, for Nash equilibrium, we can get in this game Nash equilibrium like this. So we have here this element to be a Nash equilibrium and this one. But for max-min, it's not possible. In this case, we'll have just this one. So there is a difference here. And we might want to check what is better and so on. Another thing that we have not discussed yet as a task, we have discussed it, but not as a task. It's like a task, a second star. It's Pareto optimal points, or Pareto optimal. Pareto optimal means that we check, it's like a Nash equilibrium, but if for Nash equilibrium, sorry, for Nash equilibrium, excuse, reconnect there. Yeah, here we check only this condition, that the value should be not less than any other. But for Pareto, we should also check that it might be less, but only. But in this case, utility function for another player should be larger. Well, the idea is that here for Pareto optimality. So if we have an element and we have another element for player one that is better for him, then it's not. It looks like it's not Nash equilibrium, and it's not. But it might be that if player one he will change his strategy, then the player two will lose something. So maybe this element is very bad for player two. In this setting, we can say that this point cannot be chosen by player one because he doesn't want to make trouble for player two. In this case, this one is some kind of equilibrium, or this point is Pareto optimal, because there is no such strategy that player can choose without loss for the second player. And we will talk about Pareto optimality later, next lecture. But so I would like you to make it as a homework, maybe Pareto optimal if you have enough time. If not, then just make max-min strategies here and compare Nash equilibrium, max-min, and stable sets of stable or lists of stable strategies after elimination, epistemic elimination. Okay, we have 1 minute before the before our lecture or our seminar today finish. So if you have any question, please ask me. I'll try to. Oh no, sorry, but you can write me. You can write to me in our chat. or you can write email. I will try to help you. So I will upload this video, and it will be available maybe tomorrow, maybe, or on Friday, and yeah. And maybe I will upload the example of my code. It's not optimal. I don't claim that it's optimal. I think that Ilya's code is maybe better. No problem. The idea is just to combine all of this. Okay. So thank you for coming, and see you next week. Okay.
Thank you so much, sir.
Goodbye.
Bye.